orthogonal projection, and orthonormal bases. Well, we have discussed this some. In fact, I will remind us the orthogonal projection that we have done. But before I do, I'm going to just remind you of many things we have discussed which are important in this section and the coming ones. Maybe I will underline some things. Well, I underlined this, that two vectors are orthogonal provided their dot product is 0. So this is the first thing. Then we discussed the length of a vector. You take the square root of v dot v. This is the length of a vector in Rn. This one I may not have explicitly mentioned, but the distance between two vectors, you just take the length of v minus w. We discussed unit vectors. We have a unit vector provided the length is 1. Well, and we discussed, and we will see today, if you have some non-zero vector, you can always make a unit vector from that just by taking the vector, multiplying by 1 over its length, and this will be unit. And then this one we discussed just if you can calculate the angle between two vectors, well, two non-zero vectors, because you see here I'm dividing by the product of their lengths, just by taking this is the inverse cosine or arc cosine of v dot w over the product of the lengths of v and w. Okay, so all of this we have recalled and discussed some, although I will do an example in a moment. These two in blue, while I may not have explicitly written on the board, but we will use this one. I will use in our very last example today, Cauchy-Schwarz inequality. Where does this come from? Well, think about it. If you think from the above, right? What's in here, and I could have written this differently, but what's inside these parentheses is a cosine of an angle. So we know in absolute value the cosine is, well, it's always less than or equal to 1 in absolute value. And so if you have an absolute value, this is less than or equal to 1, then that would say that the absolute value here is less than or equal to these two products. And these two are always non-negative anyways, they're lengths. Finally, let's talk about this last one, which we will see maybe in the next or the one after that video. Well, this really just comes from a picture. Suppose this is V, and oh, excuse me, this is supposed to be V. I wrote W. Let's suppose this is V. And then whatever W is, we know how we add triangle rule. So I put W here. This would be 90 degrees or pi over 2. And then V plus W is here. Oh, okay. This is V plus W. And you see the Pythagorean theorem says that this side squared plus this side squared equals this side squared, and that's exactly what this equation is saying. Okay, so now let's do an example. Let's do an example of using some of this before we get into orthogonal projection and orthonormal bases. Here are two vectors in R3. We want to find the angle between V and W and find the distance between V and W. Well, let's remind ourselves, we know the cosine of theta is V dot W over the length of V times length of W. And then we know the distance between, so this first part is what we use for number 1, and for number 2, as we just reminded ourselves, the distance between the two vectors is this. Okay. Well, let's begin on number 1. I need to calculate all these quantities and then think about the inverse cosine. V dot W is 2 plus 0 plus 0. The length of V is the square root of, here, 4 plus 4. This is the square root of 8, or 2 square root of 2. The length of W is here, square root of 1 plus 1, square root of 2. Okay, so maybe I need to actually erase this. I will come back to it. We will finish this problem, part 1, and then move to part 2. So I know the cosine of theta, where theta is the angle between V and W and always measured between 0 and pi, is 2 over 2 square root of 2 times square root of 2, which is 1/2. Well, now you just have to think a little bit about trigonometry. This is the cosine inverse of 1/2. And here, if you think first quadrant, I always remember you have these two here. One's pi over 6, one's pi over 3. One of them has this as the cosine, one of them has this as the sine. And pi over 6, the cosine is bigger, so that means this angle is pi over 3, because I know the one that goes with this is square root 3 over 2. So this angle is not pi over 6. The cosine is 1/2 at pi over 3. So the angle between these two vectors is pi over 3. And this is the number 1. Okay, now let's move on to number 2. Maybe I'll erase my picture that was helping me think about how to figure out theta. I need this, V minus W. And this will just be, well, first let's compute V minus W, and then I will compute the length. This gives us the distance between the two vectors. This is -1, 1, -2. Oh, I did W minus V. Well, I was looking here. V minus W. Pardon me. Reality is I would get the same length, but since I wrote V minus W, let's actually do V minus W. 1 minus 1 minus 2. Okay. And then this is the square root. It's 1 plus 1 plus 4. It's the square root of 6. So this is the distance between these two vectors. Now we'll move into the orthonormal bases. The definition, a collection of vectors. Let's say I call them U1 to UM in Rn is what's referred to as orthonormal, provided, well, we need two things to be orthonormal. We need that each vector is unit, meaning it has length 1, and the second thing we need is that they're all orthogonal. So they are all, I'll say, pairwise orthogonal. Meaning you take any two of them, any two different ones, you take their dot product and you get 0. So another way we could write this is entirely of the dot product. So in other words, this collection is orthonormal provided if I take ui dotted with uj, I get one of two things. I get 1 if I is not equal to j. Oh, pardon me. This way, 0 if I is not equal to j. Okay. Let me tell you what each one means since I started to write it wrong. Here, this is saying that you take any two different ones They are orthogonal, right? Their dot product is 0. And this one, if you have a vector dotted with itself and you get 1, this means it's unit, right? Because the definition of the length, this is maybe a comment I'll put in a box. The definition of this is it's the square root of ui dot ui. And so if ui dot ui is 1, then so is the square root. And similarly, if the square root of ui dot ui is 1, then so is ui dot ui. So saying that you take a vector, dot it with itself, and you get 1, it's equivalent to saying it's unit. Okay, that's the only time you have length 1. Okay, so this is what characterizes orthonormal collection of vectors. So, well, what are some examples? Let's speak about R3 for the moment. This E1, E2, and E3, these are orthonormal. These were our standard orthonormal. These are our standard vectors in R3, where you have a 1 and one component, 0 everywhere else. Okay, what else? These are not the only orthonormal collections. Maybe I'll just do 2. If I took okay, and that's one vector. And then how about I do both of these are orthonormal collections. Maybe I should write that. Both of these collections of vectors are orthonormal. This one might be the easiest to think about if you aren't sure about the second collection. Well, what is the length of one of these, or what is the dot product of 1 with itself if you take the square root of 2 over 2 squared plus the square root 2 over 2 squared, which is, even though this is a minus, this would be what you'd calculate for both. This is a half plus a half, which is 1, right? So this says that both of these are unit. And then you can also see here you get negative and positive of the same thing. So they are also orthogonal. So here are 2 collections of orthonormal vectors in R3. Now the next thing that I want to say, or we will actually prove, is that if you have a collection of orthonormal, I'll say it this way, orthonormal vectors in Rn, then the collection is linearly independent. And this is what will lead us to make a definition of an orthonormal basis. Okay, so theorem. Suppose we have U1 to UM, and these are orthonormal vectors in Rn. Then this collection is linearly independent. And this I will prove, okay? Well, how do you prove this? Or what is one way? And I mentioned when we first started talking about linear independence that this is one way that's very natural to prove, because one of the criteria was an if-then. And so this is how I will prove this. So suppose I have some linear relation among these vectors. And then I just need to show that all the CI's are 0. CM is 0. And this will prove that this collection is linearly independent. How do we do this? Well, here's what I'm going to do. So let's show Ci is 0. And I'm working generally, let I be some number between 1 to m. And I will show Ci is 0. In effect, then I have showed that all of this C1 to m is all 0. Okay, so I'm going to take this equation and just dot product ui on each side. So if I take ui dot this whole thing, C1, U1. Okay, this one I'm going to include, there's some little Ci, Ui in here, whatever that happens to be. And then the very last one is Cm, Um. And this will be equal to, well, I just take the dot product on this side. Okay? Now we have to think that this is what maybe I will, this is not part of my equation. This is what I'm doing. Showing Ci is 0. Okay, very nice. First, let's start with the more straightforward side, which is this side. You take any vector, you dot it with the 0 vector, you get 0. Okay, so this is 0. Now let's do this side. One thing that we have is properties of dot product, which means I can distribute this across the sum, and these constants I could pull in front of the dot product of the two vectors. So this first term will be C1 ui dot u1. And then we have C2 ui dot u2 would be the next one. Somewhere in here we have a Ci ui dot ui. And then the very last one, I gotta move my 0. Let's put the last term, it's Cm ui dot um. So this is Cm ui dot um, and this was 0. Okay, maybe it looks complicated, except we're in really great shape because we are assuming that U1 to UM are orthonormal, which means, well, it means ui dot u1 is 0. This is 0. ui dot u2 is 0. Okay, and then here, this one, ui dot ui is 1. Okay, all the way out to ui dot um, 0. So you see, these are orthonormal, which means whatever I is, when I dot ui with any other of these vectors besides ui, this one, I get 0. Okay, so what does this equation sort of actually say? Every single term is 0 except this one. And this says Ci is 0. That's Ci is 0. That's what this equation says. And so we can conclude, I did this for one, but it's general. So we can conclude that all of them are from the similar argument. And this shows the vectors are linearly independent. Now I'll make one comment and then I will define orthonormal basis. And this is so I'm done with that proof. Okay, my other comment is that I only really needed here that the vectors were orthogonal and non-zero. So if you have a collection of vectors that are all orthogonal, so you can remove the unit part, just orthogonal, then they'll be linearly independent provided you don't have the 0 vector in the set. 0 is orthogonal to every vector, but 0 is never a part of any linearly independent collection of vectors. Okay, this is really just a comment because what we're really interested in is orthonormal collections of vectors. One thing that we get from this is any collection of n orthonormal vectors in Rn is a basis for Rn. Because we have n vectors. That's how many we need in a basis for Rn. And what we just proved is, because they're orthonormal, this collection must be linearly independent. So anytime you have a collection of n orthonormal vectors in Rn, you have a basis. And it has a name. And this is called an orthonormal basis. Maybe this part shouldn't be a surprise to you. Okay. Now these are very nice orthonormal bases. We are going to be working with orthonormal, that concept, in the next couple of sections. Orthonormal bases are the nice bases that we like. Well, for instance, E1. So for example, building on what I discussed earlier, this E1, E2 to En, this is an orthonormal basis for Rn. Now let's do another example. So what is this example going to be about? Given an orthogonal basis, we may construct an orthonormal basis by normalizing each vector. Now, what does this mean? Well, here I have V1, V2, V3. They're in R3. I have the right number. None of them are 0. If I can show that if I dot product, well, let's check. Let's check. What I need to check here is that V1 dot V2 is 0. V1, I'll check it, but it should be 0. V1 dot V3 should be 0, and then V2 dot V3 should be 0. And if I have all of these 0, then I know that these are orthogonal. And none of them are 0. They're in all 3. They are a basis. But you can tell even by looking at V1 that these are not unit vectors. We can make an orthonormal basis by just taking each one and dividing by its length. Okay, that's what we'll do. So let's just check just to make sure we have orthogonal vectors. V1 dot V2 is -2 plus 2. V1 dot V3 is 3, 12, or 3 and 12, 15, minus 15, and then V2 dot V3 -6 plus 6. Okay, so in fact these are orthogonal. And then I can construct, well, just as it said. Okay, so what we need to do is, maybe I'll move a little bit this way, the length of V1, this is going to be the square root of 1 plus 4 plus 1. This is the square root of 6. The length of V2 is the square root of 4 plus 1. This is the square root of 5. And the length of V3, this is the square root of 9 plus 36, 15 squared. Let's see. We would have 15 times 10 is 150, and then 15 times 5 is another 75. So this is 225. And when we add these to 70, okay, and this is the same as 9 times, oh, so it's going to be 3 square root of 30. Okay. I don't really multiply numbers so well in my head. Okay, that was challenging for me. I should be up here with a calculator if I'm going to put numbers like that in a problem. I think we're okay now. Hopefully I didn't make a mistake. So now you see, to get the orthonormal basis, maybe at this point I will erase this. I've discussed what we are doing. It gives me space to write our orthonormal basis. My orthonormal basis is as follows. 1 over the square root of 6. Maybe I'll have a little more space. And then we have 2 over the square root of 6. And then we have 1 over the square root of 6. This is my first vector. I took v1 divided by its length. My second vector is minus 2 over the square root of 5, 1 over the square root of 5, and 0. Finally, my third vector, okay, is 1 over the square root of 30, and then 2 over the square root of 30, finally, minus 5 over the square root of 30. Okay, this collection here is an orthonormal basis for our 3. So here, maybe I'll write what I just said. This is an orthonormal basis for our 3. And I'm going to come back and use these vectors in an example in a little while. Let's move into orthogonal projection. However, we have discussed at least to project on, along a line. And we did this carefully when we were talking about, well, rotation, reflection, projection, scaling, things like this. So, what is this? Well, if L is the span of a vector W for W not equal to 0 in Rn, then we take some vector X in Rn. We had the following, the projection it's along the line, which means the projection will be a multiple of W. And the multiple was X dot W over W dot W. And this defines a vector on the line L. And this was also called, or also denoted, I should say, it was this. This was the orthogonal projection. And then we also had the following. This was the component of X that was perpendicular to the line or orthogonal to the line. This was X minus the orthogonal projection. Okay? Well, what am I changing now, or what is the orthogonal projection we're talking about now? Well, it's not all that different, in fact. This is a one-dimensional subspace in Rn, and all we're changing is we're taking any subspace of Rn. So suppose V is a subspace of Rn. And we have some vector X in Rn. And then we want to define the orthogonal projection of X, well, onto the subspace V. And this will be denoted, well, we still have this notation or this notation. Okay, well, what is this? It's going to be a vector, and it's going to be a vector in V. Okay, that's the only thing that would make sense for this here. This, well, and it's very much like this. As I mentioned, this was a vector in the subspace once we projected. Well, I'm not ready to define it yet. So what I need to define this orthogonal projection is I need an orthonormal basis for V. So let's take U1 out to UM orthonormal basis for V. And now I can define this, the projection is equal to, okay, it's going to look just like this. Now, what would this formula, and we even discussed this, if in fact W was a unit vector, as all of these are, W dot W is 1, and all we would see is X dot W times W. That would be if it was unit. Well, this is what we will see here. So generally, right, to get an element of this subspace V, I need a linear combination of these basis vectors, and the coefficient in front of each vector looks like this, except understanding that each UI is unit. So it will be X dot U1, this is the coefficient, times U1, plus X dot U2, this is the coefficient, times U2, all the way out to X dot UM, this is the coefficient, times UM. And you see this projection is a linear combination of the basis vectors for V. This linear combination is in V. And then we also have this. So if this is this notation, okay, which is X minus the orthogonal projection, and this will be the component of X which is orthogonal to the entire subspace. Okay. This is the orthogonal projection. Find the projection of E1 onto the subspace with this basis. Well, we know this subspace is three-dimensional. For example, we have three things. And you notice, just by looking at this, that you can quickly take the dot product of these two, you get 0. The dot product of these two, you get 0. And then the dot product of these two, you get 0. So these are orthogonal. But then, to get an orthonormal basis, we have to go one more step. This is what we need to start with, the orthonormal basis. This is kind of like we did before I defined the orthogonal projection. We need to take these three vectors and normalize them. Well, the thing is, they all have the same length. So if I called this, say, V1, V2, V3, all of these have the same length. The length of VI is the square root of 1 plus 1 plus 1, which is the square root of 4 or 2. So all I need to do to get an orthonormal basis is divide every single entry I see by 2, because they all have the same length. So here's the first element of my orthonormal basis. Here's the second. And here is the third. Okay, so far so good. Now let's project E1, and I will find this other part, which is the component of E1, that's say orthogonal to the subspace, and we'll check, just as a first example, we'll check that in fact it should be orthogonal to the subspace. I'll make a comment on that when we get there. Okay, so if we want this, oh, E1, I know the vector I'm doing it to, the projection onto the subspace of E1. Well, I take E1, now this will be my U1, U2, U3, E1 dot U1, U1 plus E1 dot U2, U2 plus E1 dot U3, U3. This is orthogonal projection, okay? And then now we just need to compute some dot products and put, U1, put the appropriate vectors there. E1 is the vector with zeros everywhere else. So you dot product with any one of these. E1 dot this is a half, E1 dot this is a half, and E1 dot this is a half. So this is going to be a half. And then I put U1 here, which is all a halves. Okay. And then this is another half, E1 dot U2. And then 1/2, 1/2, minus a half, minus a half. Finally, 1/2. Here, it's going to be 1/2, minus a half, minus a half, a half. Okay, now what happens when I add all of these together? This would be my final answer here. 1, 2, 3/4. Then I have a fourth, 2/4 minus a fourth is 1/4. 1/4 minus a fourth, and minus a fourth is minus a fourth. Oh, I'm running out of space. And then a fourth minus a fourth plus a fourth, this is 1/4. Okay, so this is my vector like this, which lies in my subspace. Well, of course it does. It's a linear combination of these basis elements. Now, maybe I'll erase my orthonormal basis. I'll leave my original basis. And just for this first example, let's compute, as I mentioned, this one. You take x minus the orthogonal projection, and it's this. And this should be perpendicular, orthogonal to the entire subspace. Well, here we go. This is a 1 in the first location, zeros everywhere else. So I take 1 minus 3/4, I have 1/4. But then there's zeros everywhere else, so the other entries of this difference are just negative what we see here, negative a fourth, positive a fourth, and negative a fourth. Okay. Now, this is an important observation. This should be orthogonal to V, the whole subspace, which means we take any vector in the subspace V and we dot product with this one and we get 0. But really, to verify this or justify this or realize this, I should say, any of those, we just need that this vector is orthogonal to each vector in a basis for V, because Well, every vector in V may be written as a linear combination of the basis vectors, and if you take the dot product with a linear combination, it would be, you could write it in terms of dot products with these, with, well, some coefficients. But if these all dot to 0, then you would get 0 for every single vector in V. So let's just think about that here. If you take this and dot with V1, well, a fourth minus a fourth, a fourth minus a fourth, 0. Dot it with V2. You have a fourth minus a fourth, minus a fourth, 0. Dot it with V3. Here we have 2 fourths, minus a fourth, 0. Okay? So in fact, this is orthogonal to the subspace V. Let's make, well, an important observation. If the vector x is already in V, the projection of x, well, into V, what would this possibly be? You are already in the subspace and you project into the subspace. You just get back the vector, okay? Now, why is this an important observation? Well, it actually is more important than it seems at the moment. So what is this observation leads to the following. If you have U1, U2, now I'm going to go all the way out to UN. This is a basis for Rn. And I should add orthonormal. Basis for Rn. Okay, well, let me make a comment before I use this. What did we talk about at the very end of our basis video? At least I think it was that video. If you have a basis, then every vector in your vector space can be written uniquely as a linear combination of the basis elements. We know, so given x in Rn, we know we can write x uniquely as a linear combination of ui. This is combination of this, that's what I just talked about, of this basis. We can find this, so we can find this unique way to write it. We can find, and I'll even tell you what it's called. They're called the coordinates of x with respect to this basis. Easily. Using this idea of projection, because we know that x is in Rn. Therefore, it will be equal to the projection. Uh-oh, I didn't mean to put that lower. The projection here. This is using this observation, right? And then this equals, well, x dot u1 plus x dot u2 out to x dot un. And these are what's called the coordinates with respect to, or you might also see relative to, this basis. This is coordinate 1, coordinate 2, coordinate 3. Okay, well, excuse me, coordinate n, coordinate 1, coordinate 2, coordinate 3, out to coordinate n. Okay, because they are the coefficients that appear in front of the basis vectors in this linear combination. It's very much like, and I'll do an example in a moment, but let me take you into what is this like. It's very much like this. We have this. Maybe I'll just do it in terms of 4. we think of the coordinates of this vector as we are looking at it as x1, x2, x3, x4, right? We're good. But in light of this observation, this is x1, e1 plus x2, e2, x3, e3, x4, e4. In fact, this is definitely the case that this and this is equal. And so you see these x1, x2, x3, x4 are the coordinates of this vector with respect to the standard vector basis. But if you have a different orthonormal basis, then whatever this coefficient is here, 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 etc., it would just be called as the coordinates of x relative to or with respect to that basis. Okay, now I'm returning back to this orthonormal basis. This was one that we did, right? And I said I'm returning back to it. Here I have. But, so this is an orthonormal basis. Maybe I should write that. We showed and we calculated this is orthonormal, or is a orthonormal basis for R3. Okay, then we're going to find the coordinates of this vector relative to this basis. Okay, all we need to do is calculate. So maybe I'll say C1, the first coordinate is x dot, let's say this is U1, U2, and U3, like this. This would be x dot U1. And this is, okay, here we go. It's 1 over square root 6. Oh, well, this is all over square root 6. It's 1, 4, 3. We have 8 over the square root of 6. And then C2, this is going to be all over, well, I'll write it, x dot U2. This will be all over the square root of 5. We get minus 2 plus 2. Oh, this is just 0. And then C3, this is x dot U3. Here we go. It's going to be all over the square root of 30. And we get 1 plus 4 minus 15, negative 10 over the square root of 30. Okay, so my coordinates with respect to this basis are here. This one, this one, this one. Okay, in that order. Maybe I'll just write as a final observation here that x is equal to, we have 8 over the square root of 6 times this first vector. And then minus 10 over the square root of 30 times this third vector. Like this. And you should, in fact, check. It's not even that hard. Just if you add these up, you get x. You get 1, 2, 3 as the vector. So this is an example of finding these coordinates relative or with respect to some orthonormal basis. Let's make another note or comment about the projection onto a subspace. And that's that if you take, this is for V, oh, I need my hat, for V, a subspace of Rn, and X in Rn, this map, which sends X to this vector, is a linear transformation. Just like we had when V was just a line. And well, for instance, we found the matrix. We found the matrix when you're going from R2 to R2. We had this little 2 by 2. In any case, generally this map is a linear transformation. Let's call it T. Okay, what do we know? We know the image of T is V itself. But then what's interesting is the kernel, this has a name. This is what's called the orthogonal complement, I'm missing something, complement of V. And this is what I'm defining here, orthogonal complement of V, and this is denoted like this. And this is read V perp, V perp. Okay? And if we want to write this as a set, this is the set of all x in Rn such that, well, x dot v is 0 for all v in V. But just as we discussed, it's also equivalent to say that x dot v is 0 for all v in a basis of v. Okay, I've been 2 examples ago. But this is what the orthogonal complement of a subspace is. Now, what can I say about this? Maybe I'll write this as a theorem. First of all, this 1 is a subspace of Rn. Why is it a subspace? Well, look, it's the kernel of a transformation. And we know kernels of transformations and images of transformations, for that matter, are subspaces. And this will be a transformation. The corresponding matrix is n by n. It's a transformation from Rn to Rn. And so this is inside of Rn, and this is inside of Rn. For example, what else do I have to say? If you take V intersect V perp, if you have not seen what this is, this symbol means it's every element that is in both. So this is a set, and, well, to be in this set means you are in V and you are in the orthogonal complement of V, or V perp. This is just 0. Okay, what else do I want to say about this? If you take an orthogonal complement and then you take its orthogonal complement, you get back the original subspace. And the final thing is about dimensions. That the dimension of V plus the dimension of V perp, maybe I need parentheses, equals n. This one comes from rank nullity theorem. Here's our first example. This is a vector in R4. V is one-dimensional. We are going to be looking for a 3-dimensional subspace in R4, which is the orthogonal complement of V. So we need to find 3 vectors to have a basis. And you notice I don't say anything about orthonormal basis or anything like that, just some basis. So how could we possibly do this? Well, what do we know? We know, let's say x is x1, x2, x3, x4. Then we must have, if x is in, oh, I should put that. Oh, if x is in V perp, we must have that 1x1 plus 3x2 plus 1x3 minus 1x4 is 0. This is the dot product of this and this, right? Okay, well, because I'm going to be moving into more than just a one-dimensional subspace B, notice this is this. Okay, I won't put a hat because it is just a number in this case. But what we see here, look, this is really, if you want to think about it, you can think about it as this is a 1 by 4 matrix, and this is a 4 by 1 vector, and it's saying that this vector is in the kernel of this matrix, right? Even though it's just a vector, this one. But I will move to one where it's not just one vector. Okay, now, if we think about this as a matrix and we think about finding its kernel, we have 1, 2, 3 free variables. So I would just, maybe I'll do this here. Say x2 is r, x3 is s, x4 is t. And then I know x1 must be, well, here's the equation. I could even look here. I was just interpreting it in terms of a matrix product below. I would know that x1 better be minus 3r minus s plus t. So a general vector in VPerp, okay, is minus 3r minus s plus t, r, s, t. And then to find the basis, oh, this doesn't look all that great. I can just break this as r times minus 3, 1, 0, 0 plus s times minus 1, 0, 1, 0, and then plus t times 1, 0, 0, 1. Okay, so in fact, that I do still have room on the board. I can put it right here. What we see here is that my basis for VPerp is minus 3, 1, 0, 0, minus 1, 0, 1, 0, and 1, 0, 0, 1. And you can check, maybe we should, minus 3 plus 3, okay, minus 1 plus 1, okay, 1, 0, 0, minus 1. Okay, those are all definitely in this orthogonal complement, and then we have 3 of them, and then you can argue they're literally independent, for example, by looking at their pattern of zeros as we have done before. So in fact, this is a basis for the orthogonal complement. Let's do one more example like this. Well, here's another example, and if we just look at this, these 2 vectors are literally independent. So V is going to have dimension 2, and it's in R3. We should expect that VPerp has dimension 1. Okay? And the other observation to make is that X is in VPerp if and only if, okay, put X here. Well, I want to have the dot product with like this, just like in the last example, right? I know that X dot this is 0 and X dot this is 0, but I can translate that if I 0, 3, 1, and then minus 1, 2, 4, right? Because this is 2 by 3, 3 by 1, this would be 2 by 1, but here, dot product with this gives you this entry, 0. Dot product with this entry, 0, right? So this is what I need if and only if this matrix times this vector X equals 0, or equivalently, X is in the kernel of this matrix, 0, 1, 3. minus 1, 2, 4. Okay? This is why I was thinking about the last example, even though my matrix was 1 by 4, which is really just a vector, but I wanted to think about it like that because when you have more than one vectors, it's very similar. Now, the nice thing is, we know how to find bases, or a basis, for a kernel of a matrix. Okay? I need to perform elementary row operations to get this into reduced row echelon form. Then I can figure out a basis for the kernel. So the first thing I'm going to do is I'm just going to interchange my rows so that I have a non-zero entry in the 1, 1 position. So technically, I have already done something here. I went from here to here. Oh, okay, maybe I'll write it. Well, no, I'll just do this. I've done something. Okay. I interchange row 2 and row 1. Now I'll do my first step that I write what it is. I multiply row 1 by minus 1. This becomes 1 minus 2 minus 4. This has not changed. Now I need to multiply row 2. I could have technically done it in the same step. Okay, it's fine. I'll do it in 2 steps. Multiply row 2 by a third. And this will turn this into a 1. 1/3 row 2 times and times. Okay. And then I have 1 minus 2 minus 4, 0, 1, 1/3. Well, I'm almost to reduced row echelon form. I just need to make this minus 2 that's above this 1 a 0. So I can take 2 times row 2, add it to row 1. And then I will be reduced, oh goodness, row echelon form. So row row 2 has not changed. Row 1, 1, 0, and now comes fractions. Well, it's going to be 2/3 minus 4. This is 12/3 minus 10 over 3. Okay. So this is this entry here, minus 10 over 3. You see, I have my third column corresponds to a free variable. So if I set, let's say I set x3 to be t, and then I get x1 is 10/3 t, and I get x2 is minus a third t. So an element in the kernel of this matrix is 10/3 t minus a third t and t. Okay, now I can use this to get a basis. I just need one of these. That's not 0 because this is one dimensional, and you see I had only one free variable. I'll write it up here. I could also just use 10 minus 1 and 3. It sort of avoids having a fraction. And this will be a basis for the orthogonal complement of this V. And in fact, you can check dot product here, 0. Minus 3 plus 3, 0. And then this is going to be minus 10, minus 2 is negative 12, plus 12, 0. So this is one non-zero vector, linearly independent, is perpendicular to both these. Well, and we're looking for something of one dimensional, so we have found a basis for the orthogonal complement of V. There is a comment that I want to make here, which we have observed in these 2 examples. And then I'm going to do an example that seems really different than the ones we've just been doing, but it's very much like one in your homework and uses that Cauchy-Schwarz inequality that I started the lesson with today. Okay, so what's my comment? Well, suppose A is n by m matrix. Okay, I think that's, maybe I don't need to write that. It's a matrix, and it's n by m. N rows, m columns. We can define, I will say, the row space of A as the span of the rows of A. Or I should say the row vectors. Oh, I'll just say it this way. And this is denoted like this, row of A. This is a subspace. In, well, let's see. We have n rows. Each row lives in Rm because we have m columns. So this is a subspace in Rm. Okay? Now, what we see in the last two examples is much more general. So what we saw in the last two examples is the following. Then, if you take this subspace and you take its orthogonal complement, this is the kernel of A. In fact, this is how we just had a vector or two, depending on the example, how we actually found a basis for its orthogonal complement. We just put it in the rows of a matrix. And then we found the kernel of that matrix. But this is sort of an observation I wanted to make. One more example that, like I said, it seems different than the ones we have done today, but it's similar to one in your homework. Of all unit vectors in R4, find one where the sum of the entries is maximal. Well, we have to think because it seems strange. So let's just write down some things. And as I mentioned, this will use Cauchy-Schwarz, and we will be able to figure this out. So let's suppose we have x1, x2, x3, x4. Say this is here. Maybe I should have called it u, but I'll just make it unit by here. Because we're really only looking at unit vectors here. What does this say? We want the sum of the entries to be maximal. We want to maximize this x1 plus x2 plus x3 plus x4. And we want to find the vectors such that this is maximal. But if we notice here, this is a dot product. So this is just x dotted with here 1, 1, 1, 1. Okay? And then what else can we know? We know or can use Cauchy-Schwarz, which says anytime you have a v dot w in absolute value, it's less than or equal to length of v times length of w. Right? Mentioned this at the beginning. This, which is x dot in absolute value, is going to be less than or equal to, well, the length of x times, what's the length of this? Square root of 4, which is 2. Well, maybe I'll write it in 2 steps. 1 plus 1 plus 1 plus 1. And this is, the length of x is 1, and this is 2. So the biggest in absolute value that this can be, the biggest this can be here is 2. And the smallest it can be is minus 2, right? Because if absolute value of x is less than this, it means that this number itself sits between minus 2 and 2. So the biggest this sum can be is 2. If we take a half, 1, 1, 1, 1, this vector is unit. Well, you can either calculate the length or just realize we took a vector, non-zero, divided by its length. Of course it's unit. And satisfies which is the maximal. Satisfies, if you add up all the entries, you get 2, which is the biggest this can possibly be by this Cauchy-Schwarz. So this would be the answer. To the question.